Hi everyone, I am Balamurali Murugesan. Welcome to my presentation, Prompting Classes, Exploring the Power of Prompt Class Learning in Weekly Supervised Semantic Segmentation. Computer vision task finds application in different domains including self-driving and medical. Some of the specific tasks are image classification, object detection, and image segmentation. Deep learning networks have shown promising results in all these tasks. However, preparing the ground truth for this task is tedious. Particularly, segmentation requires more effort compared to classification and detection. What if we could take the labels from classification and train a image segmentation network? That particular paradigm is called weakly supervised semantic segmentation. The process of using classification labels to prepare a segmentation network. The notion behind this is to train a deep learning classifier and obtain a discriminative regions in the image, contributing to the prediction. These regions are called class activation maps. These CAMs could be later converted to pseudo labels and be used to train a fully supervised segmentation network. One of the recent development in deep learning is contrastive language pre-training, or simply called CLIP. It is used to learn a representation between image and text and has shown encouraging results, especially in generalization. The CLIP architecture consists of an image encoder and text encoder. Image encoder takes the target image, while text encoder takes the probable classes as input. The correlation of the feature map between these encoders will provide the classification prediction, and the maximum correlation corresponds to the winner class. CLIMS showed that CLIP can be used to refine the class activation maps, and it's achieved through loss functions LOTM, LBTM, and LCVS. In case of LOTM, it focuses on improving the object, and in terms of LBTM, it focuses on removing the background, and in LCVS, removing the co-occurring backgrounds. For example, in case of LOTM, the image encoder will take image multiplied cam, whereas in LBTM, image encoder takes 1 minus cam multiplied image. So the text encoder takes a photo of train in both these cases. Now to remove the co-occurring background, for example, railroad in the case of train, for that cam is multiplied to the image and is given to the image encoder, and a photo of railroad is given to the text encoder. In our work, we found that changing the prompt given to the text encoder affects the class activation maps, which can be seen in this figure. We also found that class part of the prompt has higher impact on the CAM generation. Moreover, the class names provided in the dataset may not be the best class for generating the CAM. With this information, we proposed a simple solution to have a better CAM. A bit of background here. Let's say D is a dataset with X being input image and Y being the image label. And obtained CAM is denoted by P with multiplying the weight of particular each class, and then the feature map obtained from global average pooling. The CLIP model visual encoder and text encoder is denoted by FV and FT respectively. A typical prompt is given by a context token followed by class name token and end by a punctuation. X into PK is to focus on the object, X into 1 minus PK to related background. The text embedding of the respective class is given by VT, and the object and the background embedding is given by VIO and VIB respectively. The similarity between the object to the text and the background to the text is given by SOO and SBO. The loss function ensures that PK covers the object and excludes the related background, and is given by the following. An entire overview of our proposal is given here, and it's a three-step process. In the first step, class activation maps are generated for an input image. In the second stage, the related words for the target class is obtained. CLIP is leveraged to obtain the correlation, and we take the instance with the highest correlation. And finally, with the updated class, a glimpse is again applied where we are increasing, maximizing the foreground and minimizing the background, and we get the updated GAM. As an example, for the class boat and this particular image, yacht and sail are the other possible alternatives, and we do a correlation and select yacht, and that yacht will be later used as a text prompt to improve the GAM. So the solution is called prompt class learning. Here, for each class, we get m closest words denoted by the list S, and we generate m plus 1 potential text prompts, which is denoted by the list T, and then the embeddings with respect to all these text prompts is given by the list V. The similarity score between these text embeddings and object visual embedding is obtained through cosine similarity, and the one with the highest is picked as the target class. Coming to the results, we show that compared to the prompt tuning techniques, co-op, default, target optimization, our method is better. We also show that we get better cams, and after refinement, also we have better results. And we also show that compared to other state of the methods in weakly supervised setting, we get better results in Pascal VOC. These are some interesting observations here. The figure on the left shows the percentage of cases where the class from the ground truth is the considered instance after correlation. It can be seen that classes like sofa, dog, TV, monitor, most of the time the original class is not used. In the right side, we have compared our method for different corpuses and different number of related words. ChatGPT provides the best possible corpus, and as we increase the number of possible words, we get better results. In a qualitative comparison, we can see that compared to glimpse, our method provides better activations. Like you can see that in person and dog, second and third row. To conclude, modifying the input prompt in clip impacts the CAM generation. Replacing the class token in the input prompt has greater impact on the performance than modifying the context. A class token associated with the actual image ground truth need not necessarily yield the best CAM. Our approach 4 learns the category name that produces the highest correlation between the image and the corresponding text prompt. And we also showed that our method achieved the best results on Pascal VOC dataset in weakly supervised setting. Thank you for listening our presentation.